Yes,
Can you
it
see
has come
that?
now. Yes.
Yes, sir.
Mm.
Yeah. It's
Yes,
all
sir.
right?
Yes, sir.
Okay.
Yeah,
Fine.
it is coming.
It's coming. Okay, fine. And my voice is clear?
Yes, sir.
Audible?
Yes,
Okay,
very
okay,
clear.
okay. Thank you. Thank you.
Oh, yeah.
Okay, very good afternoon to Dr. Agarwal, Karthik, and all the participant students. In continuation of my previous lecture, today I will cover some basics of remote sensing technology. Of course, last time I gave the definition. Once again, just let me repeat. Remote sensing is the process of detecting and monitoring the physical characteristics of an area by measuring its reflected and or emitted radiation at a distance without being in physical contact. That is the basic principle. We are more concerned in this remote sensing of the Earth features from space satellites. See, basically there are two types of remote sensing. Last time I explained, no, there is the main source of energy for illumination of the Earth is from the sun. Okay, so that is called passive remote sensing. Okay, so we take the energy, whatever is falling on the Earth, and it is getting reflected. Of course, part of it gets absorbed. All the other things I will explain later. So basically, there is a source which and the reflected energy only is sensed by the satellites. So that is called passive remote sensing. For examples are typical optical cameras, some spectrometers, radiometers. Okay, it can be any range. It can be optical or in the microwave, infrared, microwave, all that range. In case of active remote sensing, the satellite itself carries the source of energy actually. For example, a radar, synthetic aperture radar, it transmits microwave energy in pulses, and the scattered radiation will go back to the satellite, part of it, because it will get scattered in all directions. So whichever radiation get scattered into the direction of the satellite, that will be sensed. So basically, it has its own source. It can be a radar, it can be a lidar also. For example, lidar is a laser radar ranging. So it can be just send a laser beam and then scattered again back to the satellite. That will be sensed. So these are all active sensors. So coming to the basic passive sensors, passive remote sensing, as I said, the basic source is the sun. Okay, it can be sun, of course, it can be earth, because sun, of course, this is the basic spectrum. Okay, coming from the sun, and the maximum is in the visible range. Maximum energy is comes in the visible range, which is visible to our eyes, and slightly beyond this is the infrared region, and further it goes into micro millimeter waves, etc. So basically, the amount of radiant flux you must have studied in physics is dependent on the fourth power of the absolute temperature. So the energy is equal to sigma into sigma is the Boltzmann constant, T to the power of 4 watts per meter square. That is the amount of energy. You want to make any calculations, there is a quantitative remote sensing. So you have to quantify how much energy is coming and falling on the earth, how much is reflected, how much energy is reaching the sensor and the satellite. Okay. That type of calculations for that, you have to take this. Second important formula is that Wien's displacement law. Basically, depending on the temperature of the body, okay, any body, it emits radiation. The peak radiation will be at this wavelength. Okay, by this formula. For example, sun, which is at 6,000 degrees Kelvin, okay, the lambda will be at 4.483. It's almost bluish green wavelength. That's where the peak comes here. Okay. Similarly, the Earth, which is at normal room temperature 27 degrees, which is nothing but 300 degrees Kelvin, the lambda will be in the infrared region around 10 microns, 9.6 microns. So here it will emit the radiation at 10 microns. Here it's not because of temperature, there is no reflection or sunlight. The earth gets heated up and in turn it emits the radiation. So that is the radiation we sense. And some of the satellite sensors, they operate in the infrared region also. I will explain those things later. So as I mentioned last time, I showed this. See, the radiation coming from the sun is the full radiation will not reach the earth actually. because in the atmosphere there are a lot of constituents like ozone, okay, water vapor, oxygen, and different types of other gases, etc., carbon dioxide, etc. So they absorb some of the radiation. So these are all absorption bands. We call it absorption bands. And whichever, this is the basic radiation. So whichever is peaks are there, these peaks are there. These peaks only we have to select for the remote sensing. So because they go through the atmosphere. So this is more expanded here, same thing to explain. So for example, right from the visible to infrared to microwave, even microwave also, there are some absorption bands. So basically most of the bands energy bands are absorbed by water molecules actually. Water can be in the form of water vapor, precipitation water, okay, that type of things. And ozone also absorbs part of the radiation. So basically our spectral bands, what we select for remote sensing on the using the space, okay, we will select bands within these ranges. See, the basic mechanism of this sensing, remote sensing, is a slightly complex one because it's not straight, radiation comes from the solar sun to earth and it goes to the sensor. Because in between you have atmosphere, you have clouds, okay. So because what happens is, depending on the wavelength of radiation, part of it gets reflected by clouds, and in the atmosphere there are so many particles, okay. So those particles scatter the radiation. Those will also go into the space, and part of it will go into the satellite also. Atmosphere is scattering, okay. So it's a combination of these things. So basically whatever we are getting the final radiation, see, we are supposed to get, our interest is to measure the radiation coming from the various features on the earth, whether it is from agriculture, water, or even some urban areas, whatever it is, we want to get see the reflectance coming from those places. But in addition to that radiation, this is scattered radiation, okay, we call it path radiance, okay. The path radiance also goes into the sensor camera. So there are algorithms to define, okay, to compute those radiances and subtract that radiance. Particularly, for example, in the case of ocean sensing, as I mentioned last time, for the potential fishing zones, we have to sense the ocean color. So ocean as it is, the radiation is very low. So what we do is we use the two bands in the infrared region. They totally absorb the energy. They don't reflect at all. So whatever the camera output coming in those two bands is purely from the path radiance only. There is no reflection from the ocean. So that energy is only from path radiance. So those two bands data output will be taken as the path radiance, and that will be used for computing the other radiances. So based on the selection and whatever bands to be selected, okay, these are all the standard bands we use for remote sensing. In fact, in our ISRO cameras, whatever cameras we have flown in our ISRO remote sensing satellites, these are all the spectral bands. Okay, we call it spectral band. It's a range of wavelengths. Okay, 0.45 to 52. This is basically a blue band, which is sensitive to chlorophyll. This is the application. Why this band is used is given here: coastal water mapping, etc. 52 to 59 is a green band, so green reflectance from healthy vegetation. 62 slightly red color, actually it's a red band, then which is also sensitive to chlorophyll and plant species identification, etc. And this is near infrared band, 0.76 to 0.9. So here also water body, because I said water will reflect less, so you can easily identify water bodies. Then vegetation vigor and biomass determination. This is called shortwave infrared band, SWIR, SWIR, shortwave infrared. This band is very useful in water stress. Okay, suppose the water is the plant is dying because of water stress, so that will be detected much earlier in this band. And another important is snow cloud differentiation. Okay, snow, for some of the bands, both snow and cloud, they look white, but this infrared, shortwave infrared band, this will be differentiate. Actually, snow will look darker and the cloud will be brighter. This is another band for discrimination of, mainly for geological applications. This band is used. And this is thermal infrared. We call it thermal infrared. This is the band. The radiation is coming from the Earth's emission, actually. Okay, here. So this one is used mainly for surface temperature mapping, including sea surface temperature is one of the major applications. So this sea surface temperature is useful in identifying the potential fishing zones. In addition to color, the chlorophyll color, we use this sea surface temperature in combination of these two will identify the potential fishing zones. Of course, these are all very, some with the bandwidth, okay, spectral bands. Whereas there is another type of sensors, hyperspectral sensors that I will explain later, that will have more number of narrow bands. See, for example, our cameras, they used maybe 4 band cameras. Okay, later we removed this band and added, okay, again 4 bands only. The Landsat satellite of NASA, they have used all these bands. Okay. So coming to the techniques of remote sensing, okay, again there are different types. Of course, broadly we can classify them into optical and microwave regions. Okay, again based on the earlier diagram I showed, passive and active. In optical also there are same active and passive sensors. The active example is a LiDAR, laser ranging and laser ranging, and passive is under push-broom, different types of cameras. This I will explain in detail. Similarly, microwave, you have active is a radar, and synthetic. This is example of radar is scatterometer, altimeter, scatter. Okay, these are all the types of different types of radars. Under passive, again under microwave, okay, again the Earth emits. Okay, Earth emission is there in the passive also. So in the microwave also. So the passive radiometers come under passive. Examples are Madras is another name of the payload, and total rain mapping mission, okay, long track scanning radiometer. This type of radiometers are used for passive sensing in microwave. So let us address first optical remote sensing. Basically, optical remote sensing is imaging of Earth features in visible and infrared range. Then we use electro-optical cameras, or we call it scanners, and spectrometers. Okay, they are the types of imaging payloads. Okay, we call them payload. In any satellite, okay, once we fly this type of instruments, that becomes the payload for that satellite mission. So these payloads, they operate. They are actually they are designed as per user requirements. Whatever user wants, what is the resolution? That I will explain. See, they are they are designed using 4 R's actually, 4 resolutions. I will explain. These images are converted into digital data. Once the image is taken, first the optical signal is converted into electrical signals, analog signals. Then it is converted into digital data, and the digital data is modulated and transmitted to the ground station through an RF link. And this received data is converted back to images. Again, you demodulate and all the processing, and again the original image is formed, processed through data processing. And of course, they use some enhancement techniques in the data processing to improve the quality of the image, and they are supplied to the users. The 4 R's I said. Okay, what is quality of optical remote sensing is expressed in 4 resolutions. Basically, any satellite image, optical image, if you take, it will tell 4 resolutions. One is spatial resolution. What is spatial resolution? Smallest size of objects that can be resolved in the image. Okay, what is the smallest thing you can see? Similarly, spectral resolution is bandwidth of wavelength range used in the imaging process. Radiometric resolution is number of discernible signal levels, gray levels, okay, in an image. And the temporal resolution is how frequently you observe the same area. Okay, this is temporal resolution. I will explain one by one. You see this here, this is a INSAT image, VHRR image. Here the resolution is 1 kilometer. Okay, from 36,000 kilometers orbit, you are taking the picture of the India, okay, mainly for meteorological applications. But here the resolution is 1 kilometer. Here, one of the IRS satellites, remote sensing satellites, you have a 23-meter resolution here. So you can just vaguely see some of the roads, okay, even the airport runway, some of the water bodies, okay, etc. You can see some bridges and all. This is a 5-meter resolution. where you start seeing the clearly the air runaway, including the markings. Some aircraft are parked here. Okay, this is the resolution image you can see at 5-meter resolution. This is a 30 centimeter resolution. Okay, where you can see even cars, vehicles, okay, everything, buses, etc. You can see. So this is the spatial resolution. We call it. This is a very high resolution. This is a low resolution image. This is a high resolution image. How you get the resolution first of all? See, this is the basic diagram. This part, including the optics and detector, okay, this makes the camera. Okay, this camera is put on a satellite, and the satellite is going like this in the orbit. So you go on imaging. See, the detector basically nowadays we are using last so many years. In fact, we are using an array of detectors. It's not single detector. We have one line array of detectors. It can be some 20, 48 pixels or 4K, 6K, 10K, like that, different number of pixel size. So it have there is a pixel. This is the pixel of the camera, that detector pixel, and you have the lens or a mirror to focus the ground image onto the detector, and it has this optics will have some focal length. Okay, in the focal plane only you put the detector, so it focuses on the detector. So the satellite is basically flying at an altitude of h. Okay, maybe it can be 600 kilometers or 700 kilometers. Some kilometers altitude it is a satellite is flying. Okay, so now with this geometry, what will happen is you take one detector, one pixel in the detector. Okay, it will be in size, dimensions of microns. Okay, maybe some 10 micron, 12 micron, something like that, different types of detectors. So this 7 micron pixel through the optics, if you project, this is the resolution you get, one resolution element. This will be generally in terms of, as I showed, meters. It can be 5-meter resolution, 1 meter, whatever it is. Okay, that is the resolution. So how do you get mathematically resolution R is equal to pixel size D into altitude H divided by focal length. Okay. Of course, you should be careful. All units should be in same units actually, because this will be in micrometers, this will be in kilometers, and normally focal length will be some few millimeters. Okay. So you convert everything into same units and calculate the resolution. So basically, what is happening here? Okay, here it's a rescue. See, now our aim is this figure should be lower. If you want high resolution, okay, I want 30 centimeter resolution, like that, half a meter resolution. So you want to reduce this figure. To reduce this figure, what you have to do? Either reduce this pixel size, okay. Instead of 10 micron size, you use 5 micron. Today, our mobile cameras, okay, they are using 1.5 micron pixel sizes actually. Whatever camera is there inside the mobile phone, okay. So that is the type of otherwise you reduce the altitude, you come down, okay, come down altitude. Okay. Instead of 800 kilometers, you fly at 400 kilometers from Earth, you will get high resolution image. Or increase the focal length. Okay. This is another parameter. So that means high resolution means, see one more, why you have to increase the focal length, I will tell you. High resolution means small area. See, instead of this size, let us say compared to a kilometer, 1 kilometer by 1 kilometer, if it is 500 meters or some 30 meter, as you are reducing this area, the radiation coming from this is also reducing. So because of that, radiant flux is proportional to the area of pixel. So we need large size optics to collect more radiation for high resolution images. That is the reason you have to put a bigger optics, mirrors, etc. to get high resolution. Naturally, with the size of the optics, the focal length also increases. That's why you get a higher focal length. Other way is high resolution needs a short exposure integration time. Okay. Here again, this while it is scanning, where the satellite is going like this, it is scanning line by line. So to the time taken to scan one line, okay, for example, one line, that is called integration time. Okay. So as the size is reducing, resolution is increasing, the time reduces. So there are techniques to use Okay, other than these techniques, okay, increasing this reducing pixel, etc. There are two types, two techniques whereby you improve the resolution. Okay, that is called, one is a time delay integration, okay, detector, and a step and stare technique. I will explain this next slide. And as I mentioned, of course, high resolution satellites, particularly strategic defense satellites, etc., they are launched into low orbit, altitude orbits. Okay, that's why they are launched. Of course, they don't tell anybody. So they launch at very 300, 400 kilometers, where they can see very clear, high resolution images. See, the time delay integration is, instead of single line, this detector itself will have number of lines. Okay, this is called stages. It can be some 40, 50 stages type of thing. So what happens is, the same area line is imaged by first this line, second this line, third line, like that it will say. Okay, as satellite is going, it will see in by all the stages, one by one after the other. So effectively what happens is, this particular pixel, for example, first line has got this signal. This is the electrical signal, let us say, charge. Light is converted to charge. So some little charge is generated. You add that to the next line. This charge you add to this charge. Okay, whatever is on. Again like that, add to the third line, add to the fourth line. Okay. So as you see, the charge is increasing. That means signal is increasing basically. So this signal, if you convert it into again digital output and all that, you get a higher, better signal to noise ratio, what we call signal to noise ratio. Other way is step and stare. See, for example, this is the satellite. Okay, the satellite is going in this orbit. Okay. So nominally, what we do, we image, the down near. Normally, we image at the nadir. Nadir we call, just below the satellite ground, whatever ground is there. That only will image and the satellite will go. But in this case, for example, you want to see this area with a high resolution. What we do, we turn the satellite when it is here itself, look ahead, okay, and then it will continuously rotate by looking this area only, okay. So basically the velocity, the ground velocity is reduced, okay, and thereby improving the resolution. That is another way of technique. This is called step and stare technique. Next resolution is spectral resolution. Okay, after spatial resolution, we go to spectral resolution. Spectral resolution is, as I said, the bandwidth of the spectrum. How much bandwidth? For example, this camera, as I showed, these 4 bands, okay, of IRS camera. This camera we call it. You can see there are 4 bands, lenses, 4 lenses and 4 detectors, etc. So each band will pass this much spectrum into the lens. 45252, 5 approximately 70 nanometer bandwidth will be transmitted through this optics, and this sensing will be done. Whereas there is a panchromatic camera. Okay, the panchromatic is nothing but a black and white camera. You get we use 0.45 to 0.9 micron, that is 450 nanometer bandwidth is used. See, normally when you go for high resolutions, another criteria is you reduce the bandwidth, spectral bandwidth. Basically, you are reducing the energy going into the sensor. Naturally, the signal will be less. So they narrow the band. The spectral bandwidth. The resolution also depends on that. So with you have here a very large bandwidth of 450 nanometers. So this is how panchromatic cameras, normally 1 meter, half meter resolution and all, that will be done, imaging will be done with high resolution in panchromatic camera bands. There is a third spectrometer. Okay, this I will explain at a later stage, but right now, here what happens is, you must have done some experiments in your physics laboratory with using a prism, for example, a prism or a grating. Okay. Once you put in the white light, you will get the spectrum, full spectrum. Okay. Full blue, violet to red you will get. So this spectrum is put on a detector. Okay. So what happens is, very narrow spectral bands imaging will be done with a spectrometer. Okay. This has many advantages actually, particularly for some applications like crop identification, etc. Okay. You have in a Like in India, in a land, you will have multiple crops. So if you use this, it will simply average the signal and give it. Whereas here, from the spectral, each crop will have different reflectances. So from this, you can identify which is the crop. So this is spectral resolution. See, for example, here, this is a panchromatic camera image. Okay, it's a black and white. Here it is multispectral, okay, visible, infrared, near short wave infrared, thermal infrared. Same features will give different phenomena in different colors. This is the hyperspectral. Okay, you will have actually the hyperspectral will be some 250, 300 bands like that. Here only 4 bands, whereas here you will have multiple because it's a full spectrum. So you have full spectrum. So you go on making small bands, then you will get any number of bands. The third resolution is the radiometric resolution. See, any image you take, okay, once you convert it into a digital, nowadays most of the cameras are digital cameras, so you get digital output. So that is expressed in terms of number of bits, for example. Okay, if you have only, let us say, 1 bit, if you just express this image in 1 bit, there will be only 2 gray levels, 0 or 1. So all white will be showed 1 and 0 will be dark. Okay? Only 2 levels you will see. If you go with the 2 bit, you get 4 gray levels. Some more data like that. 4 bit means 16 gray levels. 8 bit means 256 gray levels. Okay, small variations you can see. So this is radiometric. The higher the number of bits, okay, the higher the radiometric resolution. See, for example, when you get any digital image, okay, from the satellite, that will be in in the terms of serial pixel numbers wise the data will come. So again, with that you write a photo film system or in a computer, you put it the image back. So you will have these digital numbers. Okay, so each digital number you divide in the grayscale. Okay, 0 is black and your saturation white is 255 for a 8-bit system. So depending on the number, you put that intensity level. Okay, that's how you get these images. So that is called radiometric resolution. Next is the temporal resolution. Temporal resolution is how often a sensor can obtain imagery information of a particular area of interest. Okay. See, this is specified in terms of repeativity and revisit. There are 2 different parameters actually, these 2. Repeativity and revisit, I will explain. For example, our ISRO satellites, ResourceSat, it is having a 24 days repeativity. WatchSat is 2 days, CartoSat 1 day. Our VHRR, okay, which is from the INSAT, every 3 hours you get, it will take image of the Indian region. For example, here it is a diurnal, okay, INSAT VHRR, every 3 hours you take earth image, particularly during the cyclone effects, etc. Of course, this frequency will be much higher. Every half an hour they take image. Okay, so that is the repeativity. It can be a seasonal, for example, some areas, particularly for crop and all that. Okay, it has to be seasonally you have to vary. So maybe some once in some 20 days, 30 days like that, you can take the images. In some changes which are very slow varying changes, still you can take images annually and differences. Or it can be long term. Okay, suppose some water body has changed its course or that type of things. You can study over a period of 30 years. What are the changes in the land features? Like that you can study. So basically, the repeativity, how it happens is, see of course the satellite goes, okay, whenever it goes over the earth, it will take images. So suppose today morning 1 orbit it has gone over this area, okay, this area. This is the orbit, and then it goes to down the earth, and again goes back and comes again. So because earth is rotating, this to make 1 orbit around the earth, it will take about 100 minutes. So in 100 minutes, so earth has rotated. So the satellite comes again here. It will the earth instead of this area, it will cover this area. Okay? So this separation between these two will be approximately, depending on the orbit, etc., around 2,700 kilometers, 2,800, 2,700, 2,800 kilometers. The shift will be there. So the repetitivity, how it happens is, the width of this each image, we call it swath actually. The width of this image you take, okay, and then divide this distance divided by the swath, that approximately gives the number of days. So for example, repetitivity in days is equal to 2 pi Re by n into s, number of orbits per day. S is the swath, Re is the radius of the earth. Okay, so that's all. See, I'll just show you one. So this is how all the So this is how actually the whole globe will be covered. Okay, once this is over, again it starts filling the gaps now. That is a repetitivity. In case of revisit, what happens is, suppose this is the day one. Today it has passed, it has imaged this area, this satellite. After another 5 days, it will come very close to this. Maybe it is separated by around 500 kilometers of that order, let us say. Then what happens is, the satellite will be tilted, and again you see this area. You image this area. Again, after another 5 days, it will go slightly away. Okay. Again, you tilt it this side and see this area. So basically here, the revisit, okay, what we call revisit, is 5 days again. So it can be repetitivity is by orbit itself, revisit is by mission planning. Okay, so now I'll go to the techniques. As I showed, of course, the basic parameters, okay, before I explain, some of the parameters which we come across in the optical remote sensing technique is the focal length. As I mentioned, long focal length gives high resolution pictures. The F number, okay, you know F number in all the cameras, normal cameras, you will have an F number. F number is nothing but the ratio of focal length to the aperture of the camera inside. So the small F number means a large aperture. So you get higher signal, more light will go inside the camera. So you operate at F numbers depending on the camera design. Other one is integration time, okay, time during which radiation is collected by the sensor in one scan. Signal to noise ratio is ratio of average signal to RMS noise. Okay, this is a statistical parameter basically. Okay, and we monitor this after launch also using onboard some lamps we'll put for calibration. Using that lamps data, we compute this IFOV GST. See, there is a resolution, spatial resolution is a slightly loose term. Okay, we call we use it generally if I explaining this is a 30-meter picture resolution picture, this is 1-meter resolution picture, like that. But technically the resolution is explained in terms of IFOV, instantaneous field of view, or ground sampling distance, GST. Okay, this I will explain. Then swath is the width of the image strip. That is one IFOV element, 1 pixel into number of pixels, that gives the swath. So if you take any remote sensing camera, basically what are the elements of the remote sensing camera? You have imaging optics, okay, which will see the earth and take the images, pictures, and that image is formed on a detector assembly. It can be a line array, linear array, or it can be area array also. Okay, it can be different types, but these are all state devices. So once the light falls on these generate signals, analog signals. Okay, that analog signal is amplified and processing and all is done, and finally it is converted into digital output. The digital output is modulated on a carrier, and depending on the volume of data, okay, the data rate, okay, it can be in megabits per second or gigabits per second, that will be transmitted to the ground. So this is one, and in addition to this optics, electronics, basically of course detectors also come under electronics. You have mechanical, okay, mechanical is basically the structure, camera structure, how you build. Of course, this is a typical standard structure, but we have cameras like, for example, this is our LIS camera, IRS LIS camera, 4-channel, 4-band camera. So this is, the structure is designed with the aluminum structure, okay, welded structure, and these 4 bands, 4 camera lenses are mounted on a vertical plate here. The most important thing is all these 4 lenses, okay, their axes are parallel. So they should be parallel within a micron, actually, within a micron, very sharp, very high this thing stability, because all the 4 bands will see same image on the ground. Okay. So if one goes here, another goes here, then there will be a distortion, and band-to-band registration we call it. Okay, each band-to-band registration will not happen. So that is a very important design criteria for this type of mechanical. And here is that panchromatic. Here lenses, here is a mirror, a large mirror, and this is the structure, very stable structure. Normally we use composite fiber glass, CFRP material for this cylinder, structural cylinders, etc. So a lot of mechanical engineering also is involved in this. Now coming to with the cameras, there are 2 types of scanning, okay, from the space, from the satellite. One is the line scanning, as I explained earlier. There is a line of
Venkata, just 1 minute. Can you just explain a little bit more on panchromatic and multispectral? I think that
yeah, actually that
is coming.
Basically, that's what I explained earlier.
Yeah.
Basically, multispectral is it corresponds to, let us say, spectral resolution. Okay, of course, these 2 are related to spectral as well as spatial resolution. Spectral resolution is you have in the visible band, let us say blue to blue, green, okay, red, etc., infrared, etc. So in that you take some range of wavelength. As I mentioned, 70 nanometer bandwidth. If you take, okay, so this is the one blue band, green band, red band, like that. There is a filter actually in front of each lens. There will be a filter. That filter will allow only that band energy only. It will reflect back the other bands, other radiation. Okay, that's how you get. And I explained earlier. See, for example, blue band, what for it is used. Okay, applications wise, chlorophyll study you want to make. You want to study the water bodies, agriculture, like that. For various applications, this band data either individually or a combination of bands. Okay, they use for this. Panchromatic is basically you will not get much spectral data. The panchromatic application is mainly for high resolution and visual interpretation. You want to see what is there. Okay, whether you want to, suppose, for example, you want to build a road. Okay, what are the features there? I mean, very minute things you want to see, any buildings or any man-made constructions or artificial things and all. So for that you need higher resolution. You don't need spectral data. So you take a wide band, 0.45 to 450 nanometer band, and but resolution I want high resolution. I want to see at 1 meter or even lower. Okay, 30 centimeter image I showed. So that type of things we use it in panchromatic camera. That is the main advantage. So here, this is the line scanning basically. That means as the satellite is going like this, okay, each line is scanned at a time, okay, and after the line, okay, it will scan and go forward. Finally, the image is constructed by taking some number of lines, okay, into number of pixels. So you make a square area image, let us say, you construct on ground this image. There is another scanning technique called whisk-broom scanning. Here what happens is you have a telescope. Basically, this is a mirror actually. This is a mirror, this is another mirror, primary mirror, secondary mirror. So, and this is a plane mirror here. There is a plane mirror. This 2 combination is called some telescope. There are varieties, Newtonian telescope, Gregorian telescope, you must have studied. So basically this is a plane mirror. The plane mirror, what it does, it will whatever radiation coming from Earth, it will fall and it will reflect into this telescope. So now this mirror you scan like this. Okay, as the satellite is going like this, you scan this way, this way. So when it is here, it will see this pixel. When it is here, this end extreme, it will see this end. So here what happens is instead of array, you will have only one detector, okay, one discrete detector, one photodiode. So each pixel will be formed, okay, will that photodiode will be imaged. Okay, that means this pixel, it will see when the mirror is at one position, it will see this pixel, like that, pixel by pixel it will scan. Okay, and then when it comes here again, it will go pixel by pixel. It can be done in both ways or say one way. Okay, normally it is done in both ways. So you scan this line like this, again come like this. This is called whisk-broom scanning. Of course, in ISRO we have adopted right from day one. Okay, this is the technique we have used, and we have improved upon by selecting these detectors. Okay, to start with IRS 1A 1988 we have flown. We used a 2004 2K CCD, then 4K, 6K. We went up to 12K, and then later no device is available after 12K. So what we have done is we have butted actually. That means 12K, 112K, 112K, another 12K, like that, some number of things. Basically to improve the area of image. Okay, you can improve. This is third way of doing things. Okay, that is you have a camera. You just buy out a camera, a digital camera, Sony camera or something, okay, and that will have a area array CCD, actually area array detector, okay, and a lens built in. So you just take a snapshot, one snapshot, okay, or you take here. Normally we ensure that there is some overlap between the two consecutive snaps. So as the satellite is going, you take snapshots and cover the area. This is another type of imaging. Actually, most of the university colleges and all satellites made by universities, they use this. Okay, they generally buy a camera, ready-made camera, and put it on a small nano satellite, and this is how they do the imaging. So this is what just to show. This is a whisk-broom imaging. Whisk-broom means you sweep from here to here, then here to here, here to here, like that you sweep as the satellite is coming. Whereas a push-broom, you sweep straight away, one line, second line, third line, like that you scan it. So here, for next slide also. Next slide. So same thing, this push-broom scanning, some of the parameters I want to explain here. One is, depending on the number of pixels here, CCD array, okay, that much area you will cover. This is called swath, ground swath, okay. And in terms of angle, whatever the coverage, total coverage from this angle is called field of view. How much is the field of view you cover with this camera? Whereas this particular pixel, okay, as I mentioned earlier, resolution, the resolution is also called instantaneous field of view, IFOV. Okay, if you just project this one, this may be few, less than degree, 10 millidegrees type of thing. That is the depending on the resolution. Okay, basically you convert linear dimension into an angular dimension. That is IFOV. Then integration time, as I mentioned earlier, see the time taken for one line scan. Okay, so actually this pixel can be square or it can be some other dimension also. That is quite possible. So what we express this resolution in another term is called ground sampling distance. Basically, what happens is when you are scanning, you have a detector, okay, with one window, you are scanning the ground. Okay. So at what sampling rate you are doing, that depends on the ground velocity. Okay, see the satellite is going with a velocity of I mentioned last time, 7.5 kilometers, let us say, 7.5 kilometers per second. Velocity satellite is going in the orbit. So if you project that onto the ground, this ratio of you take, so it will be approximately around 6.5 kilometers per second ground. Okay, so that is the velocity. that velocity into integration time. This integration time will be, let us say, in milliseconds, okay, or even microseconds. So the time into this velocity, if you multiply, that is the distance you get. Okay. For example, some 10 milliseconds, and the velocity is 6.5 meter. So approximately 65 meters or so of that order, you get 65 meter resolution. That is the how. That is called ground resolution. This ground sampling distance (GSD) is equal to velocity into integration time. This is another way of explaining, giving the basic resolution. For example, this is a satellite, showing, it is imaging like this. This is the swath, we call it swath, okay, and it is imaging, of course, just pictorially showing, but it's showing in different spectral bands. So it is imaging and going like this. Now, each element, if we take, I will explain each element. For example, in the camera system, you have optics, you have detectors, okay, you have electronics, and you have mechanical systems. So coming first to the optics, we basically use two types of optical systems. One is lenses. Okay, a normal lens, you must have seen in any camera, you will have lenses. Okay, it is not one lens actually. Inside the camera, there will be multiple lenses actually. Number of lens segments will be there to improve the quality of the image, basically image quality. Okay. So this is a refractive, we call it refractive system because light goes through it and it gets refracted. So this is a refractive systems. Another one is a reflective system or even catadioptric, we call it. Reflective is basically we use a telescope system. Okay. There is a primary mirror with a central hole here. Okay, and this is the secondary mirror. So light comes here, gets reflected and again gets reflected, and image will be here. The detector will be put here. So because the basic reflective systems will have some limitations, some corrections and all to be done. So we also put some refractive lenses again here in this near focal plane. Some lenses are used to further improve the image quality, like distortion and all those things. So this is called reflective system. Most of the panchromatic cameras, okay, you take it, that you go for reflective systems. Okay, and multispectral cameras, they go for refractive system. It's 1 minute. Otherwise, it's heavily raining. I'll just close the door and come 1 minute. 1 minute. So these are the two types of basically optical systems we use. So here you can see this is a panchromatic camera. This is the primary mirror inside, and this is actually it is in the other side. This is back of the secondary mirror. Okay, so this is held with some tripod type of stand. So the light will go inside, reflect here. There is a hole in the mirror. It will go inside, and then on the back side of this there is a detector. So reflective optics basically they use for long focal length, large apertures, very big aperture, no chromatic correction. Of course, okay, just for your this thing information understanding, chromatic correction is nothing but when the white light coming. Normally in lenses, depending on the wavelength, blue light goes here. The focal plane will be slightly different. From blue to green, there will be some blurring will be there in terms of color. Okay, you can see in some of the cameras. So that will not be here because it's reflecting only. So no chromatic correction is required. Of course, here the disadvantage is field of view will be small. In reflective systems, the field coverage is small. That's why you get very, this area, once it is a high resolution, some 30 centimeter, half meter type of thing, this area will be small. Normally it will be some 10 kilometers only you can cover. Whereas if it is for other applications, if it is some 50 meter resolution type of thing, this will be of the order of 150 to 200 kilometers. Okay, area will be covered. Sometimes that auxiliary optics is required. The highly alignment, this is a mechanical wise, design wise, is see between this mirror and this mirror, if there is a distortion, the whole image quality will suffer. Okay, that's very important in this type of designs. These are our refractive lenses. Okay, They are of short focal length, so resolution will be poorer, small apertures, and correction required. So you'll have multiple lenses to do corrections. Of course, here they provide large field of view. Okay, and auxiliary optics is not required. Alignment wise, that they are not that much sensitive. And the neutral density filters are used to attenuate the input light, depending on the light entering. Actually, sometimes you have to attenuate, otherwise the whole detector will saturate. So sometimes we attenuate the light by using these filters. And these color filters or interference filters are used for passing the required wavelength band. For example, you see this is a digital camera, a typical digital camera like Sony. There are so many manufacturers. Okay, you will have the lens here, and in the detector, okay, you have this card, PC board, in which the detector itself is mounted. Okay, on the back side, other components, etc., are mounted for processing. Okay. So coming to the detectors, after optics, you have detectors. So basically, push-broom techniques uses linear or area array CCDs, while discrete detectors are used in electromechanical scanners. The outside showed Landsat. They use this type of single photodiode or maybe some 3 or 4 photodiodes. Okay, and that will be the mirror will be scanning. Whereas in line scanning, we use a linear array like this. Okay, there will be a line of detectors inside this silicon. Okay, so depending on the size of that pixel, it may be 5 micron, 10 micron, that type of things will be there, or it can be area array CCD. The advantage of CCDs is they are designed on solid state technology and smaller pixel size and high packing density. It is actually improving. Every time, year by year, we are getting earlier our own, for example, our mobile phones. They started with 4K camera like that, and 4K becomes 8K, 10K. I mean, it goes on improving. 16K camera with for a Chinese mobile phone. So that basically the pixel sizes, they are reducing like anything. Good geometric fidelity and high speed of operation. Basically, this is important. Materials what we use for making these detectors. Silicon is used for most of the visible. Okay, for all our normal cameras. Okay, the material silicon is used. For infrared, indium gallium arsenide and indium antimonide, these materials are used for low infrared, short wave infrared. And thermal infrared, mercury cadmium telluride, lead sulfide. These are all the materials used for. Okay. These materials particularly, they require cooling. Okay, because their bandwidth, band gap energy is very small. Even with the thermal energy, they generate a signal. So you have to operate these detectors at a low temperatures, almost liquid nitrogen type of temperatures. Okay, that's where actually we use these detectors in our INSAT VHRR payloads for one of the channels. So that's why we use a cooler. Okay, I will explain later. We use a cooler for that, for cooling this detector. Low temperature operation for IR detectors reduce thermal noise. Okay, either it can be a passive cooler, or of course we can use, some places we use active coolers, thermoelectric coolers also are used. The latest technology is active pixel sensor technology with CMOS readout, okay, for faster operation. And time delay, this I have already explained. See here, just to explain, basically you all know charge coupled device, okay, how it operates. You have a silicon, okay, substrate, and that you give a silicon dioxide coating, and you have metal electrode. So when the light falls on that, okay, because of the photoelectric effect, okay, the electrons are generated depending on the intensity, wavelength, etc. Electrons are generated here. Okay. So what happens in this CCD construction? If you see, these are the actual photo detectors. Okay, photo sensitive area. So here light falls, the electrons are generated below this okay, silicon. Then what happens? They transfer it. Okay, they transfer it to the shift register. All the pixels will be transferred, and then from the shift register you read one by one pixel. Okay, how they do it is, you have, let us say, this 3-stage okay electrodes. Whenever you apply a charge here on this electrode, there will be a potential well will be generated. The charges will go to the lower potential. Okay, you collect here first. Okay, then you apply here also. Then it will get shared between these two. You reduce this voltage, then they all will go under this potential. Like that, pixel to pixel they will transfer it. Finally, output will be, there will be an output with a diode. Okay. So that will capacitor, that will be read out. See, basically there are differences between CCD and CMOS. Actually today, most of the digital cameras, they use CMOS sensors, active pixel CMOS sensors, because of certain advantages. Even though noise-wise, the CMOS sensors are slightly poorer to CCD, but there are other advantages actually. So here you just one diode, all pixels will be read, will read out in serial mode. Okay, if you want to, let us say, read some 5 pixels in between, it's not possible. You have to read entire line array. Whereas in CMOS, that is possible. Okay, because each pixel is connected to an output gate. So you just whichever pixel you want to read out, that you can read out. Okay. That is how the sensor output and various options here. Actually here, scanning technique supported by CMOS sensors, it allows windowing. For example, in this you want to only read out only this many pixels. This is particularly, of course, useful in applications like star sensor in attitude control. Star sensor, you want to read only some stars, one star here, one star like that. So that around that only you can read out the pixels. You need not read out the entire array. Or you want to do subsampling, okay, alternate pixels only you want to read. Like that, you have various options with respect to the CMOS sensors. Another important application, not application, technology is this bias color filter. See, you have a camera in your own mobile cameras. Okay, you take a color picture. The moment you snap, you get a color picture. So how each pixel will see all 3 colors. This combination of RGB is whatever color you want, you will get it. Okay, you are getting color pictures just by clicking. So this one is technology behind is on each CC array sensor, they deposit a filter. Okay, like this. This is the combination of red, green, and blue. Okay, each covers 1 pixel in the below detector. So light will pass through this. Okay, and then you will get the output. But what they do is to get color for each one. See, they apply a algorithm. For example, you see here, a blue pixel is surrounded by 4 green pixels, okay, and 4 red pixels, like this. So what they do is, for this pixel, let us say pixel blue 44, okay, what you will do, you take blue contribution is as it is, the green contribution is average of these 4, and the red contribution is average of these 4 red. Okay, so they apply to this pixel those values and then put the pixel value there. That how you will get the color image actually. Coming to the electronics, okay, processing electronics. Once the signals are basically, even to operate the detectors, okay, it consists of pre-amplifiers, post-amplifiers, bias supplies. Okay, some voltages you have to supply to the detectors. Then timing logic generating.
You want to give some 5 minutes break, Venkatrao?
I don't need, but
no, for students. Students.
Yeah, okay, fine. No problem. No problem. Fine. We'll
So, Karthik, we can meet at 2:45. Karthik, students.
Yes, sir, we can meet at 2:45.
Yeah, please.
2:45. Okay, fine. I'll resume at 2:45.
Yes, sir. Yes, sir. No problem, sir. 2:45 we can make it, sir.
Good. Nicely you are giving, Venkatrao. This much speed is required for our students.
So if they understand the basic concepts, then building on that, further technologies we can explain. But it's better to understand.
So 2:45 will meet.
Yeah. Okay. Fine. I'll come back.
Afternoon, sir.
Karthik, we can start, huh?
If you are ready, sir. If you are ready, you can start, sir.
No, I'll have come back, no?
Yes, sir. Almost all are here, sir. You can start. Sir.
Okay, fine.
Yes.
So now, having addressed optics and detectors, we'll go to the processing electronics. Basically, camera electronics consists of preamplifiers. The initial signal, low signal is amplified, then post amplifiers, bias supplies, timing logic. You have to generate number of clocks to read out the data from the detectors, CCDs. Then exposure or gain control, and most of our cameras we had calibration, as I mentioned, using LEDs. Okay, so that LED calibration electronics. So increasing data rates demand high frequency operation. See, as the resolution, we are going towards higher and higher resolutions. For example, compared to a 10 meter, 50 meter, some hundreds of meter resolution, as you are going down, okay, the data rates are increasing, and also the radiometric. Also, earlier we were using 7-bit, 8-bit. Now people are going with a 10-bit or even more. So because of all these reasons, the data rates, okay, earlier some 10 megabits per second data rate we used to have. Today, the Cartosat 3 series, for example, high resolution satellites, okay, they go up to 1 gigabit per second type of data rates. So you have to have the designs, electronic designs, okay, using high frequency devices. And another demand is miniaturization. Today, everything is to be miniaturized. So the discrete devices are replaced by FPGAs and micro devices, ASICs, etc. They are using. Okay. Of course, they have their own thermal problems that has to be addressed in design. Then built-in thermoelectric coolers for IR detectors. Okay. Earlier, we used to have separate detector coolers, okay, to be attached to the detectors. But nowadays, they are available. Okay, in the commercially they are available. Along with the cooler itself, the infrared detectors are sold. Then Z-plane integration using camera on chip devices. Okay, instead of at higher frequencies, the cable lengths should not be more. So they want to put everything very close to the detector. So along the Z-axis plane behind the detector itself, they are putting the processing part of the processing electronics. Okay, that Z-plane integration. Then low noise, low ripple power supplies. That is very important. Okay, whatever DC-DC power supplies we give to the camera electronics, they should have low noise and low ripple. Otherwise, the basic signal should not be noisy. Then onboard pre-processing. Okay, of course, this is the ultimate. People are trying towards this. So you do the processing onboard itself. Normally, you send the raw data to ground, and then, as I mentioned earlier, you do some enhancing and all those things. So this, as much as possible, you process the data onboard itself, and directly you send the image data to the user. Okay, you can directly see the image on this computer. Okay, this is going to be the future. Coming to the mechanical systems of a camera design, okay, materials for camera housings, okay, basically we use Invar material. Okay. This is a type of alloy, okay, with steel and other components. So this is because this is having a very low coefficient of expansion alpha. Okay. So because of this, Invar is used, and nowadays CFRP, okay, with some particular layup of the fibers, you can achieve very low coefficient of expansion even with CFRP, but with a very low weight and high stiffness. Aluminum is also used in most of the camera construction. And low thermal coefficient of expansion to minimize distortion, and quasi-isostatic mounting of mirrors and lenses to minimize stresses. That is very important. Actually, you see, this is, for example, almost a 1 meter diameter mirror, huge mirror. Okay, of course, this is a light-weighted from behind. This is the front light face. Behind, they scoop out the material. Actually, a lot of glass material is removed. Okay, with some pockets, and this mirror is mounted on a this quasi-static mounting. Okay, something like this. They are bonded, so that the stresses won't come on the mirror. This itself will take that stress. These mounts will take the both mechanical and thermal stresses in the mirror. That is very important. Similarly, the lenses, for example, the lenses are mounted, okay, with some specific mounting techniques, 3-blade mountings, etc. Okay, so that the stresses won't come onto the lenses. The mounting material, I mean, they will take the stress. Thermal design to reduce temperature gradients within camera housing using shields and heaters, and use of baffles and hoods to avoid stray light. Of course, that is very important. In many cases, in front of this camera, okay, you will have some projection like this, which are called baffles, basically to avoid any stray light going into the camera. Then in-orbit focusing using microprofessionals for high-resolution systems. Okay, this is already attempted in one of the ISRO satellites. Okay, you have the mirrors. See, for example, one mirror you put behind a little bit of motion. Okay, some technique using microprofessionals for in-orbit. Suppose because of launch vibration or something, there is some slight change. You again refocusing onboard in-orbit focusing will be done. Then deployable very large mirrors with micro electromechanical system MEMS. Okay, that is a future telescope system. Okay, I mean, if it is not possible to have such a huge mirror on ground because of launch vehicle constraint, okay, you fold the mirror like antennas, for example. You fold a mirror and deploy it in orbit. Okay, maybe we can expect such type of systems in future. Coming to the Earth observation, most of the I have explained is related to optical, okay, up to visible range, let us say, okay, visible and near infrared, 0.8 micron type of things. So if you go further infrared, okay, up to thermal infrared, then middle infrared, short wave infrared, etc. These infrared cameras, okay, they can be independent camera, and in some cameras they can be part of one or two bands, maybe there infrared. Okay, these infrared channels are very useful for certain applications, particularly, for example, atmospheric temperature and humidity profiles. Okay, there is a type of payload flown in one of the INSAT satellites. Okay, INSAT 3D. That is a sounder. Okay, basically we call it a sounder. What happens is the radiation emitted by the Earth, infrared radiation, it goes through the atmosphere and goes into the camera. That camera will have so many channel detectors, okay, infrared range. So what happens is each wavelength, it will have different characteristics. Actually, as the signal is going through the atmosphere at different layers of atmosphere. Okay, some of the particles, some of the constituents, atmospheric constituents, they absorb, okay, that wavelength. So based on the temperature, humidity, etc. So from that sounding, they derive these parameters. Then on ground, soil water stress monitoring, outgoing long wave radiation, okay, for Earth radiation budget, okay, how much radiation is coming. Of course, this type of things, calculations are made for this weather prediction, okay, climate studies, etc. Total radiation budget, how much radiation is entering the Earth, how much radiation is going out of the Earth, greenhouse gases, what is coming again is not going out of the atmosphere, but again coming back to the Earth. Okay, that type of calculations are made. So for that also, the outgoing long wavelength radiation, okay, is important. Sea surface temperature, as I said, mentioned earlier, this is done by infrared range wavelengths. Then cloud motion vector, the CMV, particularly the INSAT VHRR, that during the cyclone, okay, for study of cyclone, they predict every 30 minutes, half an hour they measure, and which way the cyclone is going, its trajectory they will track, okay, by studying the cloud motion vector, and they give the prediction of where it will cross the coast, etc. So basically the difference is, while other cameras they use glass materials, infrared cameras use germanium for optical component. Lenses are made with a material called germanium, okay, which will pass the radiation, infrared radiation. Normal glass will not allow IR radiation to pass through. Infrared cameras use, as I mentioned earlier also, indium gallium, some certain materials, okay, with the low band gap energies. So for based on the radiation, for example, these two are used for short wave infrared radiation, and mercury cadmium telluride and lead sulfide. They are used for long wave thermal infrared 10 micron, 12 micron type of bands. These detectors are used. These detectors need to be cooled. Okay, I mentioned earlier, passive or active, okay, to reduce thermal noise. Only thing is, due to low radiation levels, the IR cameras provide poor resolution. Normally, you won't get a 1 meter or half meter resolution at all in infrared channel. Okay, infrared cameras will have, in terms of meters or even kilometers resolution. Okay, because of the low radiation levels. So these are the infrared INSAT 3D imager. Okay, you will have different type with visible band, short wave infrared, middle infrared, water vapor channel. Okay, then this is thermal infrared 10.3 to 11.3, 11.5 to 12.5. Okay, so different bands from INSAT satellites. Okay, you measure, and of course many parameters are derived from this. See, this is another payload, very high resolution radiometer, okay, VHRR, what is flown in INSAT. See, for example, this image is very familiar. Of course, till few years it was every day we were seeing on Doordarshan channel, okay, at 9 o'clock news. We used to see this image, and they will tell whether any rain, rain is expected, where there are clouds, or if there is a cyclone, how the cyclone is going, east coast, west coast, etc. So this VHRR image is taken by a payload called very high resolution radiometer, this image. So that was flown in INSAT satellites actually. So INSAT, there were two configurations actually. Originally, right from INSAT 2 series, INSAT 1 series, what we tried is, we wanted to put both the communication payload and meteorological payload on the same satellite. Okay. So then what happened, of course, these are all communication antennas, okay, for communication applications. The VHRR payload instrument, okay, as I mentioned, this thermal infrared channel is one of the channels. It whereas visible band gives 1 kilometer resolution, thermal infrared band gives 8 kilometer resolution actually. So the thermal infrared channel has to be cooled. Okay, the detector has to be cooled. So what they have used is, they have used a passive cooler. I will show you next diagram. This is the cooler actually, which is facing towards the space, okay, cold space. Space is outside very cold. So this will be radiating and cooling the detector. And this is the basic telescope, etc. So what happens is, because of that, you cannot have solar arrays on both the sides. Okay. Normally, any communication satellites will have the solar arrays on this side as well as this side. But because of this cooler, what they have done is, we have put a solar array on only one side. So because solar array is on one side, there will not be any balancing. Okay, attitude balance will not be there. So we have put a sail, okay, a sail like this, sail boom. So this will be deployed in orbit. This is a sort of dummy mass, just a dummy mass only, to balance this. So that's how, because of this, wherever this VHRR is not there, those satellites, for example, pure communication satellites, they had this solar arrays on both sides. This is when we wanted to have a combination of communication and meteorological payload on the same satellite. Okay. One more point I wanted to bring here is, see, when it is in kilometers, see, visible band 1 kilometer, infrared band 8 kilometer, why it is called very high resolution when compared to meters. Okay, when we are talking of meters or even centimeters resolution on ground, why these are called high resolution is, basically this system is from geosynchronous orbit, geostationary orbits. Okay, so that means 1 kilometer from 36,000 kilometers. Okay, so if you convert this into angular resolution, this is very high resolution actually, very 0.9 degree approximately. Okay, so that's why this is called very high resolution radiometer. So subsequently, this is what? This is the VHRR cooler. Okay. So, of course, we had some problems initially, some reflections, solar radiation falling on this and then getting reflected and entering this cooler. So, of course, those were addressed and solved later. So subsequently, we thought we'll decouple communication payloads and meteorological payloads. So the one satellite, okay, called Kalpana, that is after it is named after the Kalpana Chawla, who had that accident, Columbia accident. So in her name, this satellite is made. So this is purely meteorological satellite actually. So here, because we had put this one, okay, only solar array is put, okay, this side, and because it is a smaller satellite without any further antennas or any other payloads, we could do that balancing with a single solar array. Power requirement also was met. So this is the configuration of Kalpana 1 VHRR payload. The next is type of payloads is spectrometers. Okay, as I mentioned, the spectral resolution time I mentioned that one is with bands, 4 bands. Okay, band 1, band 2, like that, with lenses, filters, etc. Whereas a spectrometer is an imaging instrument with very high spectral resolution and a coarse spatial resolution. Okay, here the spectral band is very fine, just a few nanometer bands, but the spatial resolution will be of the order of something like 100 meters or 200 meters. Of that type of resolution only we will get in the spectrometers. See, the spectrometers are very useful for mineral exploration, vegetation monitoring, plant stress, crop residues, plant composition, hazardous materials like oil, okay, oil spills, dust, mine waste, pollutant. To study these things, okay, these spectrometers are used. Inland and coastal waters, phytoplankton composition. This is also very useful for that fishing zones, etc. In addition to the ocean, only thing is here the area coverage will be not that much as compared to ocean color. So, and study of some algal blooms, etc. So, for example, this is one algal bloom in Lake Taihu in China. We studied. Okay, some of these algal blooms are studied with a spectrometer. Here, the principle is, of course, you know that when white light enters a glass prism, okay, it gets split into a spectrum. We have done this experiment. We used to measure the wavelength, sodium vapor lamp wavelength, etc. Or white light, okay, it can be a prism or it can be a grating also. It can be a grating. Okay, here also the grating, reflective grating or transmitted grating, it gets into the spectrum. So what they do is, this spectrum is formed on a detector. So each the pixels, okay, whatever, suppose the pixel is 5 nanometer, 5 micron type of thing. In that they put these spectral bands, continuous spectral bands, and then they image. Okay, so for example, here the satellite is going is a spectrometer, let us say. So it is scanning. Of course, this is shown just to show it only pictorially. Otherwise, what happens is, for example, blue. Okay, blue continuously. This blue will be seeing first. It will, let us say, or red, for example. Red image will see first. Every line it will see the scanning. So you will get one red image, then followed by orange, yellow, like that it goes, for example. Okay. So for each spectrum, narrow wavelength, you will get one image. Okay. So that's why this is how this hyperspectral image is shown. Okay. In you will have in third dimension, this is the number of bands actually. It will be some 200, 300 bands will be there. Okay. So each band will have this image, one image. Like that, it will. This is a imaging spectrometer concept. So basically, the configuration wise, there will be some scan line. Okay, and then this will be, there will be a objective lens, and there will be a slit actually. Okay, slit, when the light passes through the slit, it becomes dispersed, and then this is a collimating. This is the dispersing element, a grating or something. So here it will get dispersed into wavelength of number of wavelength colors. Okay, the detector is put here. So this is spatial dimension actually. Here you will get 2-dimensional spatial, and in this vertical direction is you will get the lambda. So each line will be first they will see the blue, let us say, or next green, like that. Okay. So you will get number of bands, 200, 300 bands images. You will get for a given one image. Let us say some 100 by 100 kilometers or whatever it is. You will have 200 images like that. So these are all some of the images. Okay, earlier of course I already mentioned. mainly pollution monitoring, okay, mineral mapping, water quality. Okay, water quality, any contamination is there in water bodies, etc. for study. This is very useful because of narrow spectral bands, urban surface mapping, etc. Yeah, that's all. Yes, Agrawal, that's all.
Student can ask some questions.
Yeah, sure, definitely. That's what I expect.
Karthik?
Sir, are smart materials used in satellites for remote sensing? Any smart materials?
Smart materials means what exactly you are looking for?
Sir, like how it can behave with respect to temperature changes?
Yeah, smart materials means, of course, for construction, yes, not for detection, but for construction. For example, some of the materials, they are designed such that their expansion, no coefficient of expansion, is matched actually earlier itself. For example, I'll tell you one application. The focal plane, there will be a small change in terms of microns from air to vacuum. On ground, you focus, okay, the lens and detector, etc. But when the satellite goes into space, vacuum, there will be a small shift. So there are materials used, okay, which will compensate actually by heating, or they will compensate. Again, it will come back to the same focus. There are some applications, but not many actually. Smart materials we are not using much.
I'll just add something, Venkatrao.
Please.
So, smart material called the some shape memory alloy also used for deployment mechanism.
Yeah,
We have used in some of our small satellite. So that is also falling under smart material.
Yes, correct.
Okay. Okay. Other questions? Students should interact by. He has a lot of experience.
Sir,
Yeah, go ahead.
sir, can volcano activity of volcano can be used using remote sensing? Activity of
Yes, it can be seen particularly for even with the spectrometers or even with the normal cameras. Volcanoes are monitored, images, and in fact, once the volcano erupts, okay, before and after eruption, they'll study and they estimate the damage, how much lava has flown. Okay, from the satellite image you can estimate. So it is used for any, actually for any events. The satellite images are used uh, in various applications.
understood, sir. Thank you.
Yeah. Any other thing? Don't hesitate.
Venkatrao,
Anything you want to? Yeah.
I want to give some assignment to students. So, uh, can we give like individual application of satellite no payloads, different type? Let them study, search the literature, generate one report, and give some presentation if possible.
Okay. That's a good idea. Actually, that's a very good
So
idea.
at least they will come to know many applications because in a 1 hour or 2 hour lecture we cannot give all applications. Each
Correct.
students,
Yes.
so Karthik.
In fact, I have restricted myself. Each
Yeah.
area, if you take, there are again sub areas. For example, agricultural. If you take, in agricultural, there are so many applications. Okay, crop acreage monitoring, for example, or even for this one sericulture, or even for horticulture. Small high resolutions are coming now. You can see small areas like that. So there are different applications. Any area you take, there are multiple applications.
Karthik,
Yes, sir.
what I suggest we give assignment to student
Yes, sir.
telling that they have to work out one application
Okay, sir.
of the satellite.
Okay, sir.
What is the usefulness and all those things, so what kind of instruments are used and other thing, and don't make more than 4 students per group batch, because total are how many
Yeah,
students?
I'll make the batch wise.
Huh?
Then you might get around 4 means not more than 4. You can get around 10, sir.
No, 10 means how many students are there?
So actually, totally somewhere around 30 will be there. So 30 plus 35 to somewhere there.
So make, but all are not coming, I think.
Yeah, yeah, few are not coming. So I think then some have shifted also to other things. So I think according to report, it is somewhere 39 something.
29. So
39, 39. So
we can make 3 people per batch.
yes, sir, we can make 3 people per batch. Anyway,
Okay, can you please circulate?
yes, sir.
And they have to give a small 8-10 pages report,
Yes,
and
sir.
then a very 5 minutes presentation. And
Okay.
what we expect from a student is what is the application, why this is important, how it is done. Okay.
Yes, sir.
So, and any technique or something if they want to give, let them present there.
Yeah,
Sure,
right.
sir. Yes, sir.
That's good.
So that is the first assignment to all students. Okay.
Sure, sir.
So next class is on Thursday.
Yes, sir.
Thursday is 10:55. Venkata.
Yes, sir.
Okay, fine. Okay, right. I will,
So there we are going to describe
microwave. See, so far we have discussed optical, infrared. Basically, in this region, the next class I will cover microwave. Okay, there the techniques are slightly different actually.
Okay.
So what are the different types of microwave instruments? All that I will explain in the
Okay.
next class.
Good.
Okay.
Good.
Okay. Fine.
So,
Okay, Karthik. That's
okay,
all.
thank you. Karthik, you please send a note for Thursday again. Reminder
Definitely.
on Wednesday.
Sure, sir. Definitely.
Okay.
Thank you so much, sir.
Okay, thank you, Venkata.
Okay. Thank you. Right.
Thank you.
Thank you, sir.
Thank you very much.
Thank you. Okay.